Hi, I'm Zhiyang Shen from Aalto University, and I am presenting my paper titled Learning Spectrograms with Convolutional Spectral Kernels. It was accepted by the AI Stats Conference this year. My co-authors, also from Aalto University, are Markus Heinonen and Samuel Koski. I will start with a brief overview about Gaussian processes, which is our main focus. It is a stochastic process prior on functions with Gaussian marginal distributions, parameterized by mean function m and covariance function k. The covariance kernel encodes the prior knowledge we have on the function being inferred. With prior choice being critical in all Bayesian modeling problems, it is also important that we select a good covariance kernel. I include here an intuitive example of prior draws, showing that the prior space of Gaussian processes can vary wildly with a change in kernels. And in this work, we mainly study the kernel choice for Gaussian process models. Many previous works have contributed to finding flexible kernels for Gaussian processes, or in other words, replacing the default squared exponential kernel with more flexible and expressive alternatives. Here, we mainly focus on two seminal works that inspired our paper, namely the non-stationary quadratic, or NSQ kernel, and the spectral mixture kernel, or SM. The squared exponential kernel enjoys widespread usage for its simplicity, with only a single length scale parameter L, but it is restrictive in that its sample paths are often uniformly smooth, as shown by plot A. The NSQ kernel attempts to combat the issue by parameterizing the length scale as an input-dependent function, yielding the kernel function where Lij is computed with respect to xi and xj, resulting in varying degree of curvature in its sample paths. The SM kernel tackles the issue from a different angle by multiplying the SE kernel with a cosine function of a frequency parameter mu, yielding quasi-periodic patterns shown by plot C. In our work, we attempt to unify the two generalizations of the SE kernel with a larger class of kernel functions, which we name the convolutional spectral kernel, or CSK. Our derivation is based on the following feature map, which can be seen as a density of a normal distribution where the mean is complex valued. Here, mu I and Li are both functions on xi. The computation of the inner product between phi I and phi j can be solved tractably, which, just like the SM kernel, similarly factorizes into two parts denoting the input varying length scales and periodicities, respectively. And we can see from the plot that the sample path of the CSK has a rising frequency. Taking a closer look at the CSK, we can observe that it elegantly nests the previous two generalizations as special cases. If the frequency function mu I is a constant zero, the CSK devolves into the NSQ kernel. If the two functions are both constant, it devolves into the parametric SM kernel. In practice, just as the way we use the spectral mixture kernel, we can stack multiple mu and L so as to infer multiple frequency components present in the data. We can impose Gaussian process priors on mu I and Li's, effectively making the model a deep Gaussian process model, the inference of which can be done with stochastic gradient Hamiltonian Monte Carlo methods. For the second part of our contribution, I present the spectrogram as a useful tool for interpreting kernels. For clarity of the discussion, I include a brief review about the interpretation of stationary kernels. They are known to be translation invariant, in that the kernel value kxi xj only depends on the difference xi minus xj, which I denote by tau here. Rewriting the kernel as a function of tau, the inverse Fourier transform of this function gives the spectral density, or spectrum. The novelty of the spectral mixture kernel is that it effectively imposes a Gaussian mixture kernel on the spectral density, making it readily interpretable. Building on this great insight, we present the concept of spectrograms, a generalization of the spectral density that varies with respect to inputs. The Wigner transform is a non-stationary generalization of the inverse Fourier transform that yields the spectrum. In the Wigner transform, we similarly rewrite the kernel as a function of the middle point x and the difference tau, and apply inverse Fourier transform on the variable tau. Furthermore, we note that assuming a generic form of kernels taking this formula, where sigma ij, dij, and uij are functions dependent upon xi and xj, proper linearization of the functions yield a mixture of input-dependent Gaussian densities similar to the spectral density of the spectral mixture kernel. Here we demonstrate a few examples of spectrograms. The stationary SE and SM kernels spectrograms are unsurprisingly constant with respect to the x-axis, and the SM kernel's non-zero frequency means makes its sample paths quasi-periodic. The NSQ's frequency is centered around 0, but its variability along the x-axis shows its change in length scales. We can see from the second row that the spectrogram of the CSK displays a rise in frequency, consistent with the sample paths and the kernel matrix. Spectrograms can be used not only to interpret common kernels, but also to interpret deep probabilistic models. In a two-layer deep Gaussian process, for example, we first warp the input x through a function g, and then do the GP modeling on the warped input. Here we demonstrate through spectrogram that a monotonic input warping is equivalent with a Gaussian process with kernels of varying length scales. The input warping in A and the length scale function in D essentially correspond to the same spectrogram, which also produces similar kernel matrices and sample paths. From some real-world examples, we show that the CSK is an interpretable tool in Gaussian process modeling. Take this solar irradiance data, for instance, where the black points and red points are training and test points respectively. We can see from the data that it has an overall rising trend with also a rise in its frequency, which we can model with the CSK of 3 frequency components. In the plot D2, we plotted the 3 frequency components against the background of the spectrogram. We can see from the rising trend of the red component that it corresponds to the rising trend in the frequency present in the data, while the other 2 components are modeling the overall smoothness of the function. In closing, we present 2 novel contributions in this paper, namely a flexible non-parametric kernel with the capacity of modeling complex non-stationary periodic patterns, and the spectrogram as a tool to systematically interpret the spectral property of the non-stationary kernels. For more details about our work, you can check out the main text of the paper. Thank you.